Alrighty, good morning, everyone. So, just kind of recap where we finished off on Friday. So, we started talking about heat engines. We said that the heat engine is a cyclic process where we take something from a hot reservoir, draw it spontaneously down into a cold reservoir, and on the way we get that to do some sort of usable work. So, for example, run your car engine or use it to lift things, etc., etc. Then whatever's left over goes into the cold source, and then goes back through the cycle, and then this thing becomes a process. So, since the thing is cyclic, we know that the change in internal energy must be equal to 0, which means then that the work must be equal to the heat. And from here, we define what's known as the efficiency. So the efficiency then is the desired output, which in this case is the work, divided by the desired input, which is the heat from the hot source. So using this, then we can rewrite this then as what the work then is equal to the difference between the Q hot versus the Q cold, which means that the efficiency then reduces down to 1 minus the cold heat divided by the hot heat. So from this, we can rewrite the second law of thermodynamics, which says that heat does not spontaneously go from cold to hot. It actually goes from hot to cold. So in this case, we never spontaneously get it to go in this direction. We actually have to do work onto the system to get it to go from the cold source to the hot source. But spontaneously, it will go from the hot source to the cold source. And that the efficiency must always be less than 100%. So that left us with the question then, if the efficiency must always be less than 100%, what then would be the maximum amount of efficiency we can create for an engine? So we want to know what is the greatest amount of efficiency that we can actually create. And to answer that, we're going to look at a theoretical model of a heat engine, which is what's known as the Cardinal Engine. So the Cardinal Engine is a non-realistic engine in the fact that it's fully reversible, which basically means that all of the processes which are going to happen in the entire cyclic process are fully reversible, which is untrue in a realistic engine. And the reason for that is realistic engines, they have pistons, we have oil in them, but they still have friction, we lose energy due to friction, and etc. Where in the Carnot engine, everything is going to be done completely frictionless and completely reversible, which means this is purely a theoretical concept. Which means that all engines then will have to have an efficiency which is less than this particular Carnot engine. So if we can determine what is the efficiency of the Carnot engine, then we know any engine we build will have to have an efficiency less than this Carnot engine. So how does the Carnot engine work? So let's learn about the PV diagram. This is my volume, this is my pressure. So the way the Carnot engine works is we start off with 2 isotherms. So this one is going to be our hot isotherm. This is going to be at T hot. And then this one is going to be at a second isotherm, which is at a colder temperature. Let's call that T cold. So the way the Kernel Engine works is we start off up here at some point A, and then we're going to expand the gas from the volume at A. So this corresponds to this initial volume at A. Volume at A here. And we're going to expand it along the isotherm of T hot. So all I'm going to do is I'm going to expand this to some other state out here, called that state B. So I'm going to expand my gas, in this case, isothermally. Then we're going to get it to go from the hot isotherm to the cold isotherm. We're going to do that adiabatically. Okay? So then what we're going to do is we're going to expand it just a little bit more. We're now going to expand it adiabatically to point C here. So this portion here then is going to be an adiabatic process. So this is our point C. Then from point C, we are going to contract or compress our gas along the second isotherm here. So from point C to point D, so I'm going to bring this up to here. Then once I get to point D, we're then going to, again, adiabatically bring it from the cold isotherm to the hot isotherm, and this is going to be our cyclic process. So this is what's known as the Cardinal engine. So why do we do that? Well, we do that because what's true about adiabatic? What is 0 for an adiabatic process? Adiabatic process, what is 0? Heat. Good. So in this case, we know that this gives no heat. So the heat going from D to C must be equal to 0. We know that going from D to A then must also give me 0 heat, which means the only two heats which occur is this portion and this portion. Okay? So this then is going to be Q hot up here. So at this stage, I'm going to have heat flowing into the system. So this is going to be QH. And down here, this is when heat is going to flow out of the system, which is then going to be Q cold. So this is the reason that we're doing that. So the two adiabatic processes are mostly there just to ensure that there's no heat exchange in these two processes. So all the heat is going to happen just during these two isothermic. The other thing we know is that what? The work is equal to the heat in these two ranges. And the reason for that is because, remember, isothermically means that the change in internal energy must be equal to 0. And we also know that the work is directly proportional to the temperature. Because what we know is that this is equal to the number of moles times the universal gas constant times the temperature times the natural logarithm ratio of the two volumes. So this is my final volume to the initial volume. But the important thing here is that the heat is directly proportional to the temperature. Which means that as long as this is done isothermically, this temperature here is simply the temperature of the cold, and this temperature then, or this heat is going to be the temperature of the cold, and this heat is going to be the temperature of the hot. Which means that this efficiency then, for the Cardinal engine, like that E sub car, is then equal to 1 minus the cold temperature divided by the hot. So, what does this say? So the second law basically then states that what? Right, that is 3. The most efficient engine must have a efficiency less than the Cardinal efficiency, which is the most efficient between two isotherms. This is now our new second law of thermodynamics. So this just states that as long as I have a Carnot engine, well, any engine's efficiency must be less than this Carnot engine, but the Carnot engine is the most efficient I can get between two particular isotherms. The only way to make this equal to 0 is if I run the cold source here at, or not 0, but 100% efficient, sorry, is to make T cold 0. That's the only way to make this thing 100% efficient, which means it would have to run at 0 degrees Kelvin, which is not going to happen. So this is our second law of thermodynamics. So this is our Carnot. So again, any process which happens between two isotherms, they don't have to be isotherms, these have to be two different temperatures. This is the most efficient that the engine could be between these two temperatures. But since this is purely theoretical, that means in reality, all engines must have an efficiency less than this efficiency by its definition. So if we want to know the most efficient we can make it, we can first calculate the Carnot efficiency, see what that efficiency is going to be, and then we know that our engine has to be less than that actual Carnot efficiency. Okay? Let's do an example. Let's put all this stuff together and see how this all works. So, let's look at this cyclic process. So here I have volume in meter cubed. I have pressure here in simply pascals. No, I should change the units on these things. So this thing starts off here and here. So this is 2 meters cubed at 2 pascals. So my system is going to start here at point A, where the temperature at A is equal to 290 Kelvin. Then it's going to increase to this pressure of 8 with this volume of 6. This thing is going to be about here. This thing is going to increase this way. So this is, then we're going to decrease the pressure to point C here along this particular path. And finally, to make it cyclic, we're going to bring it back to point A along this particular process. So this is my cyclic process that we're going to look at. This is my heat engine. So for this problem, what I want to know is a vast many things. So part A, what I want to know is, what's the number of moles? How many moles do I have in this gas? Part B, I want to know what's the temperature at B and what is the temperature at C. Part C, I want to know what is the work equal to? What is the change in internal energy equal to? What is the heat equal to for each individual process? So meaning when I go from A to B, what's the work? What's the change in internal energy? What is the heat flow going from B to C and then finally from C to A? For part D, I want to know then what is the net work equal to? What is the net heat equal to? And also finally, what is the net change in internal energy equal to? E, I want to know what is the Cardinal efficiency of this engine? So what is the theoretical efficiency that this engine could have? And I also want to know what is the realistic efficiency. So what is the actual efficiency of this engine? And then finally, I want to know what's the change in internal energy for the entire cycle? Or sorry, change in entropy for the entire cycle. These are all the things I want to know. One thing I'll mention is when it comes to the last exam / final, when it comes to the thermal part, definitely expect to see one of these. It involves basically everything that we've done almost entirely when it comes to thermo. So let's talk about it. Let's look at part A. So how would I do part A? So put some other things on here. We also know that this is a monatomic ideal gas. I mean, come forward later. So how would I do this problem? So how would I do part A? Looking for the number of moles. So where's one place that the number of moles shows up? Ideal gas law. So what we know is that what we should be using the ideal gas law, which is the pressure times the volume is equal to the number of moles times the universal gas constant times the temperature. Now here, let's look at our process and see what we know. We know the pressure at A, we know the volume at A, and we also know the temperature at A. We know the universal gas constant. The only thing we don't know is the number of moles. Great. So let's use that. So let's say this is the pressure at A times the volume at A times the equal to number of moles times universal gas constant times the temperature at A. So from here, I can solve for the number of moles. This is equal to the pressure at A times the volume at A divided by the universal gas constant times the temperature at A. Everything here is given in the appropriate units. I don't have the unit conversion and everything, which is great. So all I have to do is plug in. And what I find is that, assuming I use my calculator right, which isn't always true, the number of moles should be equal to 0.0016. That's my number. Okay? Not too bad. Look at part B. So now what I want to know for part B is, what are the temperatures at B and C? Well, if it satisfies the ideal gas law at B, or at A, what does it also have to satisfy at B? The ideal gas law. Which means that we know the pressure at A, we know the volume at A, we know the pressure at B, we know the volume at B. The only thing we don't know is the temperature at B. So if I take a ratio of those two things, what it is at A and what it is at B, number of moles cancels out, universal gas constant cancels out, and now I just have a ratio between everything. Like it's easy. So let's do that. So here I'm going to take the ratio between what's happening at A and what's happening at B. And that the ratio of the temperature at B to the temperature at A then is equal to the ratio of the pressure at B times the volume at A, or B divided by the pressure at A, volume at A. Can't seem to speak today. So solve this for temperature at B. This gives us then that the temperature at B then is equal to the temperature at A times then the pressure at B times the volume at B divided by the pressure at A times the volume at Now, do I have to do it this way? Of course not. I could just use this guy and substitute in B, B, and B, and then use what I actually calculated for the number of moles and do it that way. I don't have to take the ratio, but again, I usually do the ratio that way. I don't have to use the number of moles that I might have calculated. So that way I get a nice, cleaner answer. Good. So let's put everything in. So this is then equal to 290 Kelvin times then the pressure at B, which is what? 8, times the volume at B, which is 6, divided by the pressure at A, which is 2, times the pressure at, or the volume at A, which is 2. So this guy's going to cancel this, makes this a 4, this makes this a 3. So this is equal to 12 times 290 Kelvin, which works out to be like 3,400 something. 80. 3,480. Just for numbers wise, that's roughly about half the surface temperature of the sun. That's why I was when you make up numbers. Okay. Okay. Great. So now if I want to know the temperature at C, how would I do that? The same thing. All I have to do now is replace all the B's with C's and life is great. So let's do that. So the temperature at C then equal to the temperature at A times then the pressure at C times the volume at C divided by the pressure at A times the volume at A. So that's it. Now in this case, the pressure at C and the pressure at A are the same, so that term is actually going to cancel. This guy is simply 3 times the size of this, so this is going to be 3 times the temperature at A. So this is then equal to 870. Okay, not too bad. So next part is calculate the work, the change in internal energy, and the heat for each of the 3 processes. Okay. So basically what we're going to have to do is we're going to have to go through each process, calculate each one of these things individually for each process. And then in part D, we're simply going to add them all together and then basically see what happens. Okay. Now, when I talked about before all the different thermodynamic processes, this is where that stuff will become important. Now in this case, the only one that we have, well, we have 2 of them. We have an isovolumetric and we also have an isobaric, but we don't have any adiabatics or any isotherms. But in those cases, if we do have an adiabatic or an isotherm, you would just look up and use those definitions that we have. What's 0, what's not 0, how do these things actually relate to each other? That's where those things will become important. In this case, we only have these 2, so we should know what these things mean in this case. But again, for this one, we're going to have to go through each one of these processes step by step. So let's do that. So let's start off going from A to B. We got all of our different processes going from A to B. So let's start off with the work. What is the work going from A to B? Now remember on a PV diagram, what is the work? The area under the curve, which means going from A to B, this is separated into these 2 different areas. Right? I have the area of the rectangle plus then the area of the triangle. So in this case, my work going from A to B is simply the area of the rectangle plus then the area of the triangle. So let's talk about the rectangle first. So in this case, the rectangle has a constant pressure. The only thing that's changing is the volume going from west. So in this case, we're going in this direction. So this is going to be a positive volume change. So it's going to be equal to then the pressure at A times then the change in volume from, call it B if we want, going from B to A. We're going from A to B. Plus the area of the triangle. So the area of the triangle in this case then is going to be plus 1/2. The base in this case, which is going to be the difference between these 2 volumes again. So this is going to be the volume at B minus the volume at A times then the height, which is the difference between the pressure at B and the pressure at A. And the pressure B minus the pressure B. So that's then my triangle. So, plugging in numbers, what I find in this case then is, that the work in this case should be about 20 joules. So this is my work. let's now look at, so we did a problem similar to this before where, remember, these two guys are related to this guy by the first law of thermodynamics, which means we have to determine one of these two guys first. Now, since this is not a special process, this is simply a gas changing its temperature, we know the internal energy then is simply related to the temperature. Right? Since we already calculated the temperatures, let's look at the change in internal energy first. So we know the change in internal energy going from A to B then be equal to 3/2 times the number of moles times the universal gas constant times the change in temperature going from A to B. So this is then going to be 3/2 number of moles times the universal gas constant times the temperature at B minus then the temperature at A. Number of moles we already calculated. We know universal gas constants. We already calculated the temperature at B and the temperature at A. So if I plug out my numbers, what I find in this case then is that this work should be, or sorry, change in internal energy should be about 63.62 joules. So this is my change in internal energy. For my heat flow, we know that what? First law of thermodynamics says that the change in internal energy going from A to B must be equal to the heat flow going in from A to B minus then the work done going from A to B, which means our heat from A to B is simply equal to the change in internal energy going from A to B plus the work done going from A to B. So in this case, since we know this is 20, this is 63.62, this then must be equal to 83.62. So this is my heat flow. Okay. So now we got that out of the way. Let's do the next stage. So the next stage now is going from B to C. So let's look at going from B to C. So going from B to C, we have an isovolumetric process. What is zero in isovolumetric process? Work, right? So automatically we know that the work going from B to C must be equal to 0. There is no work. Which means by the first law of thermodynamics, the heat flow going from A to B must be equal then to the change in internal energy going from A to B, which we know is then equal to 3/2 the number of moles times the universal gas constant times the temperature at B minus the temperature at B to C. C minus B. Again, we already calculated temperature at C, we calculated temperature at B. Temperature at B is greater than temperature at C, which means this has to be negative. So this turns out to be a negative 52.05 joules. Okay. Finally, we now want to go from what? C to A. Look at the last. C to A. So for C to A, we know that what? Again, the work is simply the area under the curve. Area under the curve in this case is simply that of the rectangle, but in this case it's negative because it's going from a high volume to a low volume. So in this case, we know that the work going from C to A is again going to be what? The pressure at A, which is the same as pressure at C, then times the volume at A minus then the volume at C. Numbers, and in this case, this should be negative 12. Oh, sorry, negative 8. That's right. Negative 8 joules. Again, change in internal energy. Going from C to A is going to be equal to 3/2 number of moles times universal gas constants times the temperature at A minus the temperature at C. Again, this is going to be negative because the temperature at A is less than the temperature at C. Right? So in this case, this is going to be equal to negative 11.57 joules. those numbers we conveniently calculated earlier. Finally, from the first law, using what we did over here, we know the heat going from C to A then is going to be equal to the work going from C to A plus the heat going from C to A. So in this case, I'm simply going to add these two numbers together. So this is going to give me a minus 19.57 joules. Okay. Oh, probably all looking at me because this is the cube. It should be a delta E. Sorry. Why are you all looking at me perplexed? Okay. And my mouse doing one thing, my brain's doing something else, my hands doing something else. All good. All right, okay? Good. All right, so good. So finally we can go to D. So D wants us to find out what is the net of each one of these. So the net is simply the sum over all of these different things. Right? So let's look at part D. I'll do that over here, I guess. So for part D, the net work is then simply equal to the sum of all the possible works. Right? So this is going to be the work going from A to B plus the work going from B to C plus then the work going from C to A. So we know this guy's 20 plus 0 minus 12. So this is simply 8. Or sorry, I keep saying 12. So 20 minus 8, which is 12. There we go. So this is 12. The net heat then is simply equal to all of the different heats. So, where should I write that? Write that down here. So Q net then is going to be equal to, so this is going to be Q going from A to B plus Q going from B to C plus Q going from C to A, which works out to also be 12 joules. My change in internal energy net is then simply equal to 0, which I could have got without actually adding all these things together, and that's because the change in internal energy for any cyclic process must be equal to 0, which is why these two things have to be equal to each other. So finally, what I get is that change in internal energy net must be equal to 0. So again, if I simply add all these things together, I would get 0. Next thing we're going to look at is what's the Carnot efficiency, and then what is the actual efficiency. So let's look at that. So part D. So let's look at the Carnot efficiency first. So we now know that the Carnot efficiency then is equal to 1 minus the cold temperature divided by the hot temperature. This is my Carnot efficiency. So from here, the only thing I have to do is go through and figure out what is my cold temperature and what's my hot temperature. The cold temperature is just what is the lowest temperature. In this case, that's temperature at A. What is the hottest temperature? Well, that's the temperature at B. So in this case, this is the same thing then, as 1 minus the temperature at A divided by the temperature B. What I also know is that the temperature of B is 12 times the size of the temperature of A, so this is actually the same thing as 11 twelfths. Because I get 1 minus 1/12, which is the same thing as 11 twelfths, which means that this thing has an efficiency of about 91.7%. This is an amazing engine. This is my Carnot efficiency. Well, what's the real efficiency? So let's look at the real efficiency. So the real efficiency is equal to 1 minus the absolute value of Q cold divided by Q hot. So basically, all I have to do then is, again, go through and look at all the different Qs and find out what is the smallest negative one, and then what is the biggest positive one. Right? So in this case, the smallest negative one is actually this guy. This is the most extreme negative. And then the biggest positive one is that one. So this is actually going to be equal to 1 minus the heat flowing from B to C, absolute value, divided by the heat going from A. I just realized I calculated the wrong one when I was trying to throw this together in my office. Anybody have a calculator?
Yes.
There you go. Plug in those numbers for me, that'd be great. So it's 1 minus 52.05 divided by 83.6.
37.75.
Good. So 37.75. Okay, the Carnot was at a whopping almost 92%, but the actual efficiency of this thing was actually closer to 38%. So much, much less than the actual, or the theoretical efficiency this thing could obtain. Good, so finally, part F. What is the change in internal energy? So for the cycle, so let's remind ourselves, what is the change in internal energy? So this is equal to the number of moles times CV times the natural log of the ratio of the final temperature to the initial temperature, plus number of moles times usual gas constant times the natural log of the final volume to the initial volume. But since we're looking at this thing as a cycle, what temperature does it start off at? 290. TA, or 290. What temperature does it finish at? TA, so the natural log of 1 is simply equal to 0. What volume does it start off at? VA. And what volume does it finish at? VA. The ratio of that is simply 1, which means the natural log of 1 is simply 0, which means the change in internal energy for the entire cycle is simply equal to 0. So, like I said, as far as the upcoming test is concerned, expect to see something like this. Okay, this is where all of those different definitions will not be important. Now for this, when it came to the change in internal energy, we used this definition. We could have also used, just to put a little note down here, we could have also used that the change in internal energy was equal to the, so this is the number of moles times CV times the change in temperature, where CV is going to be dependent on the type of gas that it is, where in this case it was a monatomic gas, which means CV is equal to 3/2 times R. So what we used here was actually CV. But if this was a diatomic gas, it would actually be equal to 5/2, and if it was a polyatomic gas, it would actually be equal to 7/2. So a lot of times it's actually better to use this one as opposed to this one, because this one is only true for monatomic gas, where this one is actually more true for different types of gases. So you actually have to know the distinction between each one of those and what each different types of CVs are. But that's it. We are done. So, having said that, I have, speaking of those type of processes, I have group assignments for you where you notice there are 2 on here. One on the front page and one on the back page, just to give you enough practice to keep working on those. These ones do have things like adiabatic and isothermal, just to give you extra practice with those different types of things. But these are group assignments, so we got about, what, 15 minutes left? Is that right? So give you guys some time to start working on these guys. So Wednesday, we will review for the thermal portion of the exam. Also bring these with you on Wednesday because we'll have time to keep working on these in your groups. And then Thursday, we'll do a review for the entire rest of the exam, so the comprehensive portion of the exam. And then Friday, we're going to take off. You guys can have extra sleep, extra time, extra hanging out when it's actually nice outside. Okay. I'll be walking around. You guys can ask questions if you have them. Anything else? You're all amazing. Don't forget, lab finals are final this week, so that'll be exciting. Yeah, these are not exam. You can talk to your neighbors. Give me all quiet. Oh. Yeah, with thermo, we almost never deal with area. So that was gonna be fine. Yes. Oh, well, for those, Max definition doesn't really work. So for example, when you're doing isotherm, you would use the definition I use over here. So what you do is that the work in that case is equal to the number of moles times the universal gas constant times the temperature times the natural logarithm ratio of one. So when it's something like that, yeah, it's hard to find the area of the curve under something like that. But that's why we did those other situations. Yeah, so that's where those other things would come into account. Yeah, so the only time you would do the area of the curve is if it was something nice like this that was very G measured. Yeah, otherwise, you'd have to do an integral and all that stuff, but we already technically did that in those definitions. Very pretty fabulous. Good news is I don't think you can ever lose that thing. So hard to get glowing, but yes. So the Adiabatic process. Yeah. So we know that actually heat flow with zeros, that means the change in internal energy is equal to the work. Yeah. So from here you can use this to figure out the volumes and the temperatures and all that different stuff. And then once you know those, then yes, you would use that into the CB definition. Okay. So, correct. Yes. Yes. So it's a diagram. That's it. Yeah. Yes. Yeah. Exactly. Okay. Which is equal to the change in internal energy. Yeah. Okay. Yep. Okay. What's up? Yes. Yes. I mean, unless you're doing a ratio. In the ratio, it doesn't matter. Yes. That's correct. Yep. 1.01 times 10 to the 10 pascals is equal to 1 atmosphere. You guys doing Taylor series? Be the most useful thing you'll ever get out of calculus. What's that? Nope. At least in physics. You guys are a little bit. Use more Taylor series than I've used anything else I've ever learned. So. This is one of the few times I'm not using sarcasm. Engineering might be a little different, but in physics we always use Taylor series. Yeah, I don't want to note card. We'll also have all of those manuals on. So you don't need to worry about bringing any of those up. Your note card is one of the technical things down. So what I needed to do for reminders. Pretty much all of them have all the calculations in them. Except for if you want to read out those,
I was wondering why I got that crazy number. Like, well, I see the 4-6 right there.
Right. Okay. It's because they're related by 10 to the 5th.
Okay.
Yeah.
So when I did my conversion,
Okay.
and then what am I doing?
What do you think? So last time it was 1.01. Why did it divide? Cross multiplication.
Right.
Thank you.
I was gonna ask.
Carson,
I feel like we have to do here, like,
oh, 8.31.
maybe this would be. It's not acidic. Oh, it is this.
Okay. And this is the isotope, right?
What do you?
And what do you look for? Oh, so the temperature, since it's isothermic, the temperature and B have to be the same. Since it's like. Okay.
But then.
Oh.
Adiabatic.
So in that case, you would just relate back to A. So for the adiabatic process, which you know is, if you go back to that page, it's the temperature times the volume raised to the gamma minus 1 has to be constant.
Okay. And we'll
And-
give it gamma or do you have to time?
Well, gamma depends on the type of gas that you have. So you have a diatomic gas, then you have the different gamma values. So for a diatomic, we wrote them down. I'm trying to remember what it was. Probably one of the things you couldn't really see in the board. So I think it's,
Oh, here.
yes, yeah. So for the diatomic, it's 7 times. Yeah.
Okay.
Good. Yeah. So you know gamma, you know the volumes at each point, so you know that we're looking for them as the temperature.
Oh, okay.
Oh, R is 8.31. That'll be on the first page. Oh, well, let's start. We don't do simple. So here we use that to
It's 2B to the gamma minus 1.
Here it has to be the same. So since you're going to the temperature there, you automatically go to the temperature there.
That equals a constant.
Here, since this is adiabatic, which you also know then the temperature here is related to the temperature here by the fact that the temperature times the volume raised to the gamma minus 1 must be constant. So in that case, you know the volume here, and here, and you know this is the gamma is 5/7. Okay. Yeah, correct. This part is- yeah, okay. Okay. Okay, so you don't need, the reason for that is what if isotope? Hence the thermal word. So good. So what you know is since this is isothermal, since the temperature is constant, how does that temperature is equal? For that one, good. So you know this is adiabatic. Right? So for adiabatic, what you know is that the temperature times volume raised to the gamma minus 1 must be constant everywhere along the curve. So since you know the volume and the temperature here, you know the volume here, you can find the temperature using this. So it must be true that the temperature at A times the volume at A raised to the gamma minus 1, and you can get the temperature at C times the volume at C raised to the gamma minus 1. And then use that to find the temperature.
I have a question.
Sure.
So I have that.
So since it's constant, it just means that here must be equal to here. So it just means that the temperature at A times the volume at A raised to the gamma minus 1 must be equal to the temperature at C times the volume at C raised to the gamma minus 1. Equal. Temperature C, volume C, gamma minus 1. Good. So in here, the only thing you don't know is TC. So it's all about the TC. So that means TC then is TA times the ratio of the volume of the ratio of gamma. Yes, because it's diagonal. Okay.
Okay, so church of C.
Okay. So
I'm confused on that constant.
okay, so the constant just means that it has to be the same everywhere along this curve. So it means if I'm looking at this point, this point, this point, this point, and this point, and this point, the temperature times the volume raised to the minus 1 must be the same everywhere along that curve. Which means that if I use the fact that we know this point and this point, so all we're doing is then saying that the temperature at A times the volume at A to the minus 1 must be equal to the temperature at C times the volume at C raised to the minus 1. Okay. So from there, the only thing you don't know is what's the temperature at C. So you can do that kind of temperature at C.
So I got that correctly right now?
But to get rid of that,
Okay.
you don't need that one. Good. So now we're going to write down TA times VA to the gamma minus 1. That's how it looks. Yeah, but that's it's a sideways alpha.
Like that? No. Okay.
Must be equal to TC,
VC.
VC gamma minus 1. So here you know what VC is, you know what VA is, you know what TA is. Exactly. So now it's called TC. Good. Well, you know, you know TA, right? TC.
Yes.
What do you TA? Okay, so you should have the TC equal to TA times VA over C. raised to the gamma minus 1. So here you know TA. TA was given in the problem. You know the volume at A is given in the problem. And you know the volume at C is given in the volume at B. Because this is isotopic. So if you wanted to replace the C with the D, so the same thing. And yeah, so you know everything there. The only thing you don't know is the flammable.
Yeah, but we're.
Well, if you're saying that it is the same as. So you guys always get confused when there's a constant. So the constant just means that it's constant everywhere. So you're just using the fact that here has to be the same as here. You're setting those two together because that is what. Make sense? Okay. All right, so we're technically done. Sure. So what that means is that one of two things has to be done. So either it is the pressure times the volume raised to the gamma must be constant, or the temperature times the volume raised to the gamma minus 1 must be constant. So this is the relationship between A and C. What you know is that in your case, we remember the temperature at C, so you know that the temperature at A times the volume at A raised to the gamma minus 1 must be the same as the temperature at C times the volume at C raised to the gamma minus 1. And then from there, you're just solving for the temperature at C, because you know the volume at C is the same as the volume at B, you're given the volume at A. And you also know the temperature at A, which you're also given. Make sense?
I will say.
Okay.
I have one.